Swayam Prabha. Digital India. Educated India.
So, last class I have discussed that how we can express this beam equation in finite difference form, and I was discussing the case when beam is resting on Winkler spring and then how to use the boundary conditions. So, this was the expression. So, these expressions which is expressed in central difference scheme, we have to apply all the nodes. Okay, so, this beam which is a finite length beam which is divided into number of nodes, okay, and this node 3 to n minus 2 we can apply this equation, but for other 4 nodes we cannot apply directly these equations. So, we have to apply the boundary conditions. So, these are the 4 boundary conditions. Due to symmetric, the slope is 0, and as we are applying the UDL, the shear force as the center is 0, and it is a free end beam. So, bending moment at the edge of the beam is 0 and shear force is also 0. So, now if I apply these equations, so that means to apply these equations we need the help of some imaginary nodes. So, these nodes are called imaginary nodes. So, this is say your 2 dash node, this is 3 dash node, and then this is your n minus or n plus 1 node, this is n plus 2 node. So, these 2 dash, 3 dash and n plus 1 and n minus n plus 2, these 4 are imaginary nodes. So, this 2 dash, 3 dash, n plus 1 and n plus 2. These 4 are imaginary nodes, because actual nodes are from 1 to n. That means, your total beam, half portion of the beam is divided by n minus 1 equal part. If you divide it to n equal part, then the number of node will be n plus 1, but here the node is given up to n. So, it is divided into n minus 1 equal part, clear, and that equal part distance is h, or you can say del h also, del x also, depending upon your requirement you can express them. So, now these 4 are the imaginary node. Now, if I apply this boundary condition which is a center, that means as I equal to 1, first node we have to apply these first 2 boundary conditions, because it is x equal to 0. So, first node if I apply these boundary conditions, that dw dx at x equal to 0. So, then I can write that w I plus 1 minus w I minus 1, this is 2 h equal to 0. So, now here w I plus 1 is I plus 1 is your second node, that is w 2 node, and w I minus 1 is the this 2 dash imaginary node, w 2 dash, that is equal to 0. So, if I apply this boundary condition, then w 2 dash will be equal to w 2. So, that means the settlement at node 2 will be equal to the settlement at imaginary node 2 dash. So, that problem is solved. Now, if I apply the second boundary condition, that is w at x equal to 0, that is 0. So, now this is E I d3w dx3 at x equal to 0, that is equal to 0. So, now I can write that E I E3 I can express them x3 minus 2 w2 plus 2 w2 dash minus w3 dash. because I am now expressing this d3w dx3 in finite difference scheme. So, this is the expression and this will be 2 h cube, that is equal to 0. So, now here I know w 2 is equal to w 2 dash. So, this 2 part will cancel. So, I can write that w 3 dash is equal to w 3. So, that also been obtained by using second equation. Now, if I apply the third boundary conditions, so that means that bending moment E I d square w dx square at x equal to L by 2, that is equal to 0. So, that is E I now w n plus 1 minus 2 w n plus w n minus 1. Okay. I am expressing these d square w dx square and I am applying these condition as nth node, because that is x equal to L by 2. That means that this is the nth node. We have to apply nth node only, and this is we have to apply in the first node, these two conditions, first node or node number 1. Okay. So, this is equal to or a square, this is equal to 0. So, I can write w n plus 1 equal to 2 w n minus w n minus 1. Okay. W n minus 1. So, this is another condition. So, we have say 4 conditions. This is first condition, this is second, this is second condition, this is third condition, and we have the fourth boundary condition, that means the shear force d 3 w dx 3 at x equal to L by 2, that is also 0. So, that is minus E I. So, this will be minus. So, I am applying the infinite difference form n plus 2 minus 2 w n plus 1 plus 2 n minus 1 minus w n minus 2. So, this is 2 h cube. So, this is equal to 0. So, now if I apply this, it is equal to 0, finally w n plus 2 minus 4 w n plus 2 w n minus 1 minus w n minus 2, that is equal to 0. And now, we have this condition w n plus 1 is equal to 2 n w n minus 1, okay, because now we have to convert the imaginary node to real node, because we have to get the equation or the relationship with the imaginary node to real node, because real node are the nodes where you want to determine the deformation. Imaginary nodes are used to use these boundary conditions. Okay. So, finally, if I So, finally, if I let me first write this in different form, that means w n plus 2 minus this w n plus 1 is replaced by 2 w n minus w n minus 1. So, w n minus 1 it is 2 w n. So, this will be 4 w n, then minus minus plus 2 w n minus 1, then plus 2 w n minus 1 minus w n minus 2. So, w n plus 2, because this is another imaginary node, this will be 4 w n, then minus this 4 w n, and this is equal to 0. This will be minus 4 w n minus 1 plus w n minus 2. So, this is my fourth condition. So, all the imaginary node are now converted to, or we get the relationship between all imaginary node to real node. So, this is the imaginary node 2 dash. So, I will get the relationship. For 3 dash, I am getting the relationship. Then for W n plus 1, another imaginary node n plus 1. So, this is the relationship with the real nodes. Here also W n plus 2 with the real nodes. So, now if I want to apply all the equations, now I can apply all the equations. So, now these equations, now we can apply all the nodes. So, from 3 to n minus 2 directly we can apply, but when we will apply at second node or the first node, then we have to use the imaginary node, or imaginary node will come into this equation, imaginary node will come. So, those imaginary nodes we have to replace with the real node, because now each and every imaginary node is replaced by the real nodes, or can be replaced by the real nodes, because we have the relationships. So, now you apply these basic equation in finite difference form in all the nodes from first node to nth node, and if in some nodes, basically these 4 nodes, when you apply these equation, the real imaginary node will come. So, those imaginary node you replace with real node. So, finally, you have the n number of equation. So, you have the n number of equation, and finally, suppose when you apply these equations, so you have the n number of equations, and then you put them in a matrix, and this is your W 1, W 2 to W n, and then you have Q I to Q I. So, this is your A matrix, or this is called the stiffness matrix. So, this is your A W, and this is your force vector, your load vector, and this is your deflection vector. A is the A matrix. So, from here you have to get the W equations. So, W equation you have to, or W values you have to get. So, you solve this equation. So, that means it will be the inverse into the load vector. So, and then you will get the deflection at every point. Clear? So, once you apply these equations on n number of nodes, so you will get the nth nodes, and now all the equations can be replaced with real node deformations. So, you will get n number of nodes, now express them in matrix, and then this is the deflection vector and the load vector. Then you solve this equation, or you can use MATLAB, or you can develop your code, you can use any solver to solve these equation, then you will get the deflection at any point. So, once you get the deflection at any point, then by using the finite difference method also, you will get the slope or bending moment or shear force at any point. For example, now you have the deflection of all the points. Now, you want to determine the deflection bending moment at point 2. So, at point 2, you express that equation, that this is your bending moment equation. So, this is your bending moment equation. So, this will be your bending moment equation. That equation you have to express at point 2. So, once we apply this equation at point 2, for example, I want to determine the bending moment at point 2. So, that means the bending moment at second node. Okay. So, the bending moment at second node will be what? So, that means this will be equal to minus E I. This is your second node, n is equal to 2. So, this will be W 3 minus 2 W 2 plus W 1. this is divided by h square. Okay. So, now you know the W1, W2, W3 and you know the h square value. So, that you put, so you will get the bending moment at second node. So, similar way you will get the shear force or the slope at any point, any node by if you know the deflection of all the points. Clear? So, now there is one question, just how you will decide the h square value. So, h square value, first you take one particular value of h, okay, or you can divide it say 20 numbers and then you will get the h value, then you will get the deformation of all the points, then you divide this number from 20 to 40, then your h will further reduce, then 40 to 80 h will further reduce, and every time you will get the deformation. Then you compare the previous deformation and the current deformation. If the difference between two deformations is very less or within the tolerance limit, then you stop there, and based on that you decide your h value. For example, suppose your previous deformation or this is current or final, this is your final deformation minus initial deformation divided by initial deformation. This should be less than 10 to the power minus 4 to 10 to the power minus 6. Okay. So, if it is within that tolerance limit, you choose the h accordingly. Understand? That means, you have to increase the division and your h value will reduce, and you will find after a certain increase of the division, your deflection value will not change significantly, or this is within a tolerance limit. So, you decide h value at that point. Okay. So, that h you have to consider for all other calculations. So, this is the way you can divide solve the finite the problem beam problem in finite difference scheme, but this is for beam with finite length. Similarly, you can use it for infinite length also by using the boundary conditions, because infinite length or semi infinite, your boundary condition will change only, because this equation will remain same, because you need the 4 boundary conditions. So, if it is a semi infinite beam, you can have the boundary condition at the your say end condition, there you can apply 2 boundary conditions, and if it is infinite. So, at infinite your deformation will be 0. Okay. So, you take a length is very high where the deformation length is very large. So, where the deformation will be 0, and definitely your slope will be also 0 in infinite conditions. So, that way also you can solve it for infinite, finite, any conditions. Okay. But this is your beam under beam on wing-class spring. Okay. So, quickly I am giving that what will be the equations if your beam on 2 parameter model. So, beam on 2 parameter model, your equation is E I d 4 w dx 4 minus b dash g h d square w dx square plus b dash k 0 w, that is q b if your q is in kilonewton per meter square and k 0 is kilonewton per meter square per meter. Okay. And if so, now here in this case, if beam is resting on 2 parameter model, so there is a difference is that you will get the deformation within the beam region as well as the outside the beam region also. So, now if this is your symmetry, this is equal to L by 2. So, now this equation is valid if your x is less than equal to L by 2, and beyond the loaded region, beyond the beam region, your equation will be k into w minus gh d square w dx square, which is the equation of a Pasternak model, because where your q is equal to 0, because we are not applying any load. So, this equation is valid if x equal to greater than 2. So, now if your beam is on 2 parameter model, so there will be basically 2 equation, one is within the beam, another is outside the beam. And the boundary conditions, what are the boundary conditions? So, here your this is E star. So, beam is under plane strain condition, say condition says, so your B will be equal to 1 and E star is equal to E 1 minus mu B square. Okay, so here remember that all the equations, this will be your E star. Okay. So, I have written only E, but these all will be the E star. Okay. So, this is E star. So, what are the boundary conditions in such case? So, now we have two equation, equation number 1 and equation number 2. So, equation number 1, the boundary condition, the shear force at x equal to 0 is equal to 0, this is your x equal to 0 and this is x equal to L by 2. So, this is shear force is 0 because we are applying the UDL and it is a free end beam, and dw dx at x equal to, that is also 0. Then moment at x equal to L by 2, that is equal to 0, and shear force at x equal to L by 2, but here is the difference. It is not 0, it is for 2 parameter model, this is the equation dw dx minus dw b dx. So, what is the difference between this f and b? F is the deformation beyond the plate region and WB is the deformation within the beam region. So, I should write this is B within the beam region, this is B and this is F within the beyond the plate region. So, this is the boundary conditions for equation number 1, and another boundary condition that at x equal to L by 2, your WB will be equal to WF. So, these 5 boundary conditions you have to use, and additional boundary condition you need to solve that equation 2, because equation 2 I have one equation that WB is equal to WF, another boundary conditions that dw dx or dw dx at, here I should write this is B and this is F at x equal to capital L. So, that means capital L is the length up to which you have considered your domain. Okay, so, you have considered your domain because this is your beam and then you have considered additional part beyond the beam, so that you will get the deformation. Then how you will decide this L? Again you have to take different L and you have to run the program, and you will find after certain length your deformation at the center will not change significantly or within the tolerance limit. So, you keep your domain according to that. Okay. So, you choose your domain according to that, that means you change the domain L value and you will find after certain L value, if you increase the L value further, then your deformation at the center will not change significantly. So, you choose that L value as your domain. So, at that domain, end of the domain, your slope is equal to 0, because your deformation will be something like this, because your this is up to the beam, this is up to the beam and then beyond the beam. So, your deformation will be something like this. So, this will be the deformation. So, that means this is your at x equal to L, where the slope is 0, okay, and this is your x equal to 0 and this is your x equal to small l by 2. Okay. So, this and this deformation, this is your W b and this one W f. After the loaded or beam region is W f and within the beam region W b. So, this is the difference. Now, you use the boundary conditions I have given. So, this is for free end condition, this is for free end condition. Free end condition when UDL is applied Q. Now, you solve these equations by using finite difference scheme, the way I have discussed for the beam on Winkler model or spring. Now, you can use different boundary conditions for different loading conditions also. So, how we can do that? Suppose we can use different boundary conditions also for different loading conditions. For example, that our next loading condition is the for the UDL I have given the boundary condition. Suppose you have a beam which is resting on 2 parameter model and it is subjected to a load, concentrated load at the center. Okay. So, how we can use the boundary condition? So, one thing I want to say that in previous condition you can use these boundary conditions or sometimes you can use W f is equal to 0 at x equal to L. That is also another boundary condition you can use. But if it is for beam under concentrated load P and it is a free end beam, because if your end condition changes you have to change the boundary condition that I have discussed for semi infinite beam. The same way you can apply this here also. Now, if it is the case, this is your x equal to 0, this is x equal to L by 2 and then how I can write these boundary conditions? So, boundary conditions, your x equal to 0 dWb dx at x equal to 0, that is will be equal to 0. Okay. Now, your shear force at x equal to 0 will not be 0 here. Okay. So, your shear force will be P by 2. So, now again here the shear force equation I have given Q is equal to x equal to 0. So, shear force equation is here minus E star I d3 W dx3. This is the equation, but this is valid for if the beam is resting on Winkler spring, but if beam is resting on 2 parameter model, then your equation will further you have to add this GH B star GH dWb dx, okay, because this second contribution is due to the contribution of the shear layer. So, that means the shear force in if it is spring, then your shear force expression is simple minus E I d3 W dx3. This is for spring, but for 2 parameter model it is E I dash E star I d3 WB dx3 plus B star GH dWb dx, and for this UDL case it is 0. So, for this you have to write 0 for UDL case, but it will be equal to minus P by 2 for your concentrated load case. Okay. So, this is your force, then again your, but as your d w b dx is 0 at x equal to 0. So, ultimately this part will be cancelled, but this is for center only, not for the edge, because for the moment, that means here also moment m at x equal to L by 2 is equal to 0. So, for the moment it is same as the Winkler's model, that means minus E star I d square w b dx square, that is equal to 0. And the fourth boundary condition, that q at x equal to L by 2, that is equal to the expression that is given, that is g h d w f by dx minus d w b by dx. Okay. So, now q expression is minus E I star E I d 3 w dx 3 plus b star g h d w b dx okay. So, that means this is your sorry, this is b star, this is b star, there will be b star here because this is b star. Remember that this is b star. So, this is also b star. So, now I am taking this value minus E I d 3 w b by x 3 plus b star g h into d w b by dx, then minus b star g h d w f by dx, that is equal to 0. And at this condition w f is equal to w b. Okay. So, that means what is the difference between this case, this is my case 1 and this is my case 2, because the more or less all the 4 boundary conditions are same. What is those 4 boundary conditions? That is my under beam under plane strain condition, the slope at the center is 0, here also slope at the center is 0. Then shear force at the center is 0, here also shear force at the center is not 0, it is minus p by 2. For UDL it is p by it is 0. Bending moment at the end is 0, here also bending moment at the end is 0, and here your shear force at the end we can express in this form, here also we can express in this form. Only the difference is at the center. In case of UDL shear force is 0, but in case of concentrated load shear force is not 0. So, that means I can write the 4 boundary conditions. This is one boundary condition, this is second, this is third, and this is fourth, and this is the fifth, and this is the sixth, or this is also sixth. Okay. So, these 2 boundary conditions, these boundary conditions we have to apply this case also, if I want to determine the beyond the loaded region. That means, for beyond the loaded region also d w f by dx at x equal to L equal to 0 or w f is 0. So, now for this case what are the boundary condition? This is the first boundary condition, second boundary condition, then third boundary conditions and fourth boundary conditions, and this is the fifth and this is the sixth, or this is the sixth. So, these are the 4 boundary conditions 1, 2, 3, 4, 5, 6, 4 for the equation number 1 and 2 more for equation number 2. And for second case, because this is for case 2 where this is 1, 2, 3, 4 and then 5 and 6, these are the boundary conditions. So, if I write in different color, this is first, second, third, fourth, fifth, sixth, sixth. So, this blue color are the boundary conditions, blue numbering are the boundary condition for case 1 and the green number are the boundary condition for case 2. Okay. So, only difference in UDL the shear force at the center is 0, but in case of concentrated load at the center shear force is minus P by 2, because we are taking half portion, that is why it is P by 2. And one thing, that in case of beam resting on spring, your shear force equation is simple E dash I d3 W by dx3, but here a second term, the contribution due to shear layer you have to incorporate, that is the second term. This is this term. This term is incorporated due to the shear layer, but for the spring this is the term where this second term is not there. Okay. So, these are the different boundary conditions, and under different loading conditions and the age conditions. So, you have to use these boundary conditions to solve the beam problem by using the finite difference scheme. So, I have finished this beams on elastic foundation part. So, next class or next class I will start the new topic, that is the design of shallow foundation. Here design means the we will find the proportion or the dimension of the foundation by using the field test data mainly, and by using the lab test data also, how we can find the dimension of a shallow foundation. Thank you.